Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 2 Higher Tier from 2025. Question number 4 is on the topic of magnetism and electromagnetism. When there is a current in a wire, there's a magnetic field around the wire. Figure 5 shows a wire passing through a piece of card. There is a current in the wire. The direction of the current is going upwards, as you can see from the arrowhead on the thick black line, which is the wire. Draw two magnetic fields on the card to show, in figure 5, to show the magnetic field pattern around the wire. So they're asking you to draw two magnetic field lines. You don't really have to draw more than that. Now, what will be the shape of the magnetic field? It will be circular, right? So it will be like that. And let's draw another one. Like that. Let me just slightly change the orientation of this. Right, that's better. Now, that should give you 1 mark for drawing two concentric circles around where the wire passes through the card. That's 1 mark. The next bit is to actually get the direction right. Now, for this, you will need to use Fleming's right-hand grip rule. And the right-hand grip rule is, imagine that's the wire. That's the direction of the current. Now, if you grip your hand with the thumb pointing up, right, that's my, and you grip the wire, right, your fingers are actually going around in this. No, it's not the right hand, it's actually the left hand. I'm thinking of the other rule, right? It should be the other way around. My mistake. Oh, I didn't want to do that. Get rid of this. Right. So if it should be the left hand grip rule, so the fingers are actually pointing away from you, so in that direction, right? Fleming's left hand grip rule, right? And that would mean the direction of the magnetic field is in this direction, right? Fleming's left hand grip rule. A student positioned a straight wire in the magnetic field between two magnets. The wire was perpendicular to the magnetic field. So if I draw that, two magnets, let's draw the two magnets. Let's say that's the north, that's the south, and this magnetic field is actually going from north to south in this direction. And the wire is perpendicular in that direction. The current in the wire, I equals 0.56 amps. The force on the wire, F equals 2.1 meter Newton. The length of the wire is, in the magnetic field, is 0.05 meter. Calculate the magnetic flux density. Now use the equation sheet. We are going to use this equation. F equals VIL. Now, while I'm writing this, I can see I made a mistake. The magnetic force, this is not Newton meter. This is milli newtons. Thousandth of a Newton. So I will have to do a conversion there. Usually these 5 mark questions, There's always a conversion. So let's do that. 2.1 millinewton. If you divide that by 1000, that will give you 0.0021 Newton. So the magnetic flux density is capital B. So let's substitute the values first in the equation. So the force is 0.0021. Now if you've forgotten this conversion, you would lose a mark, but you should be able to get the rest of the marks provided you get the rest of the parts correctly. So B, which I'm trying to calculate, multiplied by the current, which is 0.56. Usually they give the current in milliamps. In the previous papers they give it in milliamps. Here they've been tricky into giving this. This is the first time I've actually seen they've changed the magnetic force. They're forcing you to change the magnetic force, okay, multiplied by the length, which is 0.050 meters. Rearranging it, B equals 0.0021 divided by 0.56 multiplied by 0.05. That gives me 0.075. 0.075. Now the unit for magnetic flux density is capital T for Tesla. The unit of magnetic flux density is the famous Nikola Tesla. The student replaced the straight wire with a loop of wire. The loop of wire was on an axis or axle so that the loop could rotate. The student connected the loop of wire to a battery and a switch. Figure 6 shows the apparatus. This is what we call the motor effect. Okay. Now, to understand the motor effect, you need to have an understanding of Fleming's left-hand rule. Now, Fleming's left-hand rule is where you got your first three fingers, including, your thumb and the first two fingers in your left hand held in this way. This is your thumb, your first finger, second finger. This is actually the force on the wire. This is the magnetic field direction, and this is the current direction. Now, on this diagram, the magnetic field is coming from north to south, right? And the current is going to go from positive to negative. So here's your positive. So it's going along this wire in this direction through this loop. So it's going up in this direction over there. That's the current direction. When it comes on the other side of this side B, it's actually going down. Now, this side A, the loop on side A, which is perpendicular to the magnetic field, which way will it move? So the force, field, and the current. Field is from north to south. Current is actually going up. So this part of the wire is actually going to go down. If this is being pushed down, this side of the wire is actually going to be pushed up when there is a current. So it will actually spin in this direction anti-clockwise, right? That's the motor effect. Let's have a look at the question now. When the switch is closed, the magnetic forces on the loop make the loop begin to rotate. Explain how. You should refer to side A and B of the loop of wire in figure 6. So what I've just explained to you, let's go through this back again, right? Now, when there is a magnetic field between the north pole and the south pole of the magnets, right, and a current in the loop of wire will cause a magnetic field as well, right? So there's already a magnetic field between the magnets. When there is a current in this wire, in this side A, first of all, there will be a magnetic field created. That magnetic field and the magnetic field from the permanent magnets will oppose each other, right? Which causes the wire to move, right? Now, since the current is in the opposite direction in side A and B, that force or the magnetic field direction is in opposite directions, right? So they will actually move in opposite ways. One side moves up and the other side moves down, right? So let's write this properly. How do you write this answer? First point. There is a magnetic field between the poles of the magnet. You don't have to say permanent magnet, right? 2. A current in the loop of wire also causes a magnetic field. Now, third point. Since the current in side A and B are in opposite directions, the vertical forces on side A and B are also in opposite directions. Now, they're not actually asking which way it will actually move, so you don't really have to use Fleming's left hand rule to figure out whether side A is moving up or down, but it was good to actually review that so that you understand the whole process, right? So this is actually 2 points I've actually written as 1. So if this is my 4th point. 5th point, right? Explain how. Yes, actually the marking scheme is asking you to identify. So the force on side A is, let's scroll up to check, is downwards, while the force on side B is upwards. Let's see, do we need to write anything else? You should refer to side A and B of the loop in figure. So we've done that. Explain how it actually rotates because of a magnetic field in the loop of wire, which is opposing, and it's in opposite direction. Right, that's it. That brings us to the end of the question. Thanks for watching, and I will see you in the next question.